Let's now talk about this problem. Here we are given an array that may contains integers positive, negative, 0 and a sum. Our task is to find out if there is a sub-array with the given sum. For example, if you see this array, right, and the sum is 22, you have a sub-array with sum 22, right? 6 plus 13, 19, 19 plus 3, 22. And sub-array means contiguous elements. So our output is true in this case, right? For example, if I ask you to find out if there is a sub-array with sum 11, your answer would be no, because we do not have a sub-array with sum 11. However, we have elements whose sum is 11, but they are not contiguous, right? Now let's see this example. We have sum as 3 and we have a sub-array with sum 3. In this example, we have sum as 10 and our output is true because we have a sub-array with sum 10. Now please pause this video and try to write down first a naive method to find if there is a sub-array with the given sum. The idea of this naive method is going to be simple. We are going to consider every sub-array, and for every sub-array we are going to find out the sum, and then we are going to check if the sub-array sum, the current sub-array sum, is equal to given sum or not. So please pause this video and code the naive problem solution yourself. Here is naive solution to solve the problem. We are running a loop to pick the beginning element of the sub-array. Then we are running a loop to pick the ending element of the current sub-array. We consider every sub-array. For I equal to 0, we consider all the sub-arrays with beginning with I equal to 0. For example, I equal to 0, we have j equal to 0, sum becomes 5. J equal to 1, sum becomes 13. So we first consider a single element sub-array, then 2 element sub-array, then 3 element sub-array here, then 4 element sub-array, right? And at every moment we check if the current sum becomes equal to sum, then we return true. So we are going to return true when I is 1 and j is 2, right? At this point we'll return true, and time complexity of the solution is clearly big O of n square, right? Why big O? Because we may return in the middle, right, while this loop is running, and auxiliary space is clearly big O of 1. Now please pause this video and try to write down a solution that works in linear time. Let's now talk about the idea for efficient solution. It is strongly recommended that you refer sub-array with sum 0 video first, because we are going to use the similar idea. What it means is we are going to use the prefix sum concept and we are going to use hashing. So let's understand this with this diagram. If you have an array from a0 to an minus 1, and if you want to check if there is a sub-array with some given sum or not, right, the given sum says sum. So what you do is you keep computing the prefix sum, right? So you have say somehow stored prefix sums, and basically you are going to store prefix sums in a hash table like we did in sub-array with 0, right? So we are going to store sum till this point, sum till this point, sum till this point, and sum till this point, right? And so there is a sub-array from ai plus 1 to aj with the given sum. Now how do we find out the sub-array? See, if we are storing every prefix sum, right? Say we have prefix sum from a0 to ai as prefix sum 1. Now when I am at aj, I'll find the prefix sum as prefix sum 1 plus sum, because this is prefix sum 1 and this is sum. So sum total this point will be prefix sum 1 plus sum, right? So what I need to do is, for every point I need to search for current prefix sum minus the given sum, right? This value minus sum, and if I find it already existing in the hash table, then I say there is a sub-array with given prefix, with given sum. Let's understand better with this example. Let's say we have this array, right, and we have the sum as 22. So we are going to compute the prefix sums one by one. So first prefix sum is 5, we store in the hash table. Then we have 5 plus 8, 13, we store it in hash table. 13 plus 6, 19, store in the hash table. See, while we are storing in the hash table, before we store in the hash table, we search for prefix sum minus sum also in the hash table. If it is there, then we return true immediately. So at every point here also we search for 5 minus 22 in the hash table, but hash table is initially empty, so we would not find it. At this point we will search for 13 minus 22, hash table has only 5. At this point we will search for 19 minus 22, hash table has these entries, we would not find it. At this point we will search for 32 minus 22, 10, hash table has only these 3 elements. At this point we will search for 35 minus 22, right? And we find this value. 35 minus 22 is 13, and we find 13 in the hash table. So at this point we return true, right? What it means is the prefix sum, if you see for index 4, At this point, the prefix sum becomes 35. At this point, we have the prefix sum as 13, right? So if you see the difference between these two, 35 minus 13 is 22, which is our given sum. So what it means is the array, subarray beginning from this index plus 1 till this index is the required subarray with given sum. Now you have enough idea how to do it. Please pause this video and write down the code yourself. Here is implementation of the efficient approach. We have first created an unordered set in C++, hash set in Java. This side we have C++ code, this side we have Java code. Now we have initialized the presum as 0 in both the codes, and then we are traversing through all the elements. And for every element we are updating the presum, right? Then this condition I'll soon explain. This is important. This handles a corner case. We have not talked about this corner case when we discussed the example. I've written the example here. I'll talk about this. Rest of the approach is same that I just discussed. We look for presum minus sum into the hash table. If we find it, right, in Java we use contains function. If we find it, we return true. Otherwise, we insert this item or add this item into the hash table. Insert the current presum. Right, and if we never went into this condition or this condition, we come out of the loop and we return false. It means there was no subarray with the given sum. So if you see the run, we have already discussed one try run. Let's see one more example. 5, 3, 2, minus 1. We initialize the hash table as empty. We begin with I equal to 0. Presum is 5. Hash becomes 5, right? Because 5 minus 4 is not present. So we insert 5. Now 8 minus 4 is not present, so we insert 8. Now 10 minus 4, 6 is not present, we insert. Now 9 minus 4, 5 is present. So at this point we return true, right? Now why do we have this condition? And we talked about this in the other video also, where we talked about subarray with zero sum. Let's see this example. If you have array as 2, 3, 4, 6, now sum is 9. What you will do, if you do not write this condition, if you remove this condition, say, right, what will happen? You will store the presum as 2, then you will store 5. At every point you will look for presum minus 9. 5 minus 9 you will find, you will search, you will not find. 9 minus 9 you will search, you will not find in the hash table. 15 minus 9 you will not find in the hash table, right? 15 minus 9 is 6. So you will search for these values and you will never find in the hash table, right? So you will return false at the end, and there is a subarray with sum 9, 2 plus 3 plus 4, right? We have this condition to handle such subarrays that begin with index 0, right, which are actual prefixes of the given array. What happens in these cases, we do not have any previous point, so we would not find presum minus sum into the hash table, right? We need to handle these explicitly. See, one way is doing this explicit check. Another way to handle this could be we insert 0 explicitly in our unordered set and hash set, right? We add an entry for 0, right? Because you can notice here, when you have a prefix sum, when you have a prefix subarray with given sum, the 0 value would satisfy the condition. You will have the sum minus presum minus sum value as 0 at this point, right? So one way is to write this condition, other way is to explicitly insert 0 into the hash table. Let's now talk about time complexity of this. You can clearly see that this loop will run at most 10 times, right? And inside the loop we are doing constant number of operations, right? The search function in hash table is considered constant, insert is considered constant. So overall time complexity is big O of n, right? And how much auxiliary space? Auxiliary space is also big O of n. See, why I have written big O of n? Because it will run n at most time. You might written somewhere in the middle, right? Also, you might have less elements in the hash table. In the worst case, when the element is not present in the subarray is not present with the given sum, in that case you will put all the presums, right? Otherwise you would return somewhere in the middle. So this is an upper bound. N is an upper bound on space, N is an upper bound on time.